Okay, good morning. Welcome to the part B of our ultrasonic inspection. In this part, we will first learn, we will try to learn regarding the sound path. That means the sound beam profile. Ultimately, if we are considering that a piezoelectric crystal which is containing into a ultrasonic probe, it has a rectangle shape. And from that rectangle shaped piezoelectric crystal, when certain voltage of electrical pulse is impinged, it is vibrating. And due to the vibrations, ultrasound is generated with a unique frequency, that is resonant frequency. But when the ultrasound is generated from that particular piezoelectric crystal and the sound is propagating into the forward direction, the beam of ultrasound has some profile, and that profile is like that. There are three parts of that particular beam. One is the dead zone, second is known as the near zone or personal zone, and third is the far zone or front of a zone. Here we will discuss one principle that is known as hygiene principle, and the hygiene principle says that each and every point of a piezoelectric crystals is considered as a definite source of ultrasound. And when the sound will be produces, ultrasound will be produces from the each and every point of that particular crystal, it will produce some sine wave. And the interference of the sine wave with one another, there are two type of interferences there. One is known as the positive interference, where the two positive pressure region will be come together and it will increase the pressure. And if the positive and negative pressure region are interacted with it, will be known as a negative interference. And due to the negative interference, for that particular point, sound pressures will be minimum. So, from the near surface of your piezoelectric crystal, there are some area where sound pressure will be not uniform. So if we are considering this graphical presentation, then we can say that from the near surface of that particular piezoelectric crystal, there are a certain area where the pressure of the sound is not uniform. Ununiform pressure region of that beam profile is known as the near zone and it is denoted by N. Beyond the near zone, the pressure of the sound, yeah, intensity of the sound will be gradually decreases into the exponential way, that is due to the beam spread. And that is known as the far zone. If we are considering here, it is the probe crystal. So we can say in the near zones, there are multiple areas where the pressure is not uniform. And due to the non-uniform distributions of the pressure, the sizing of the defect during the inspection will be very, very difficult. And into the far zone, due to the beam spread, its nature of intensity of the sound will be changes according to the point to point. So when we will be carried out the inspection by using the ultrasonic probe, we need to know what is the near field and beam spread angle for that particular probe. The each and every probe which containing the piezoelectric crystal has a unique dimension, and according to that dimension and the frequency, we can calculate the value of near field and the amount of beam spread angle. Here we are using the near field N, and we can calculate the value of near field N equal to d square by 4 lambda, where lambda is equal to V by F. So if we are replacing the value of lambda by V by F, we can say the near field N is equal to d square F divided by 4 into V. That means near field of a piezoelectric crystals of a probe is directly proportional with its diameter and frequency. Here we are giving an example We are say here a 5 megahertz compressional probe with a crystal diameter of 10 mm. If we are calculating this one, it will come, it has a near field of 21 mm. In the same crystal, if we are considering the beam spread, then what will happen? Now, in the far zone or in the far fold, the beam will be spreading in nature. And if we are considering the central point of axis where the beam intensity is 100% or maximum, with respect to the curvature or with respect to the distance, what will happen? The beam intensity will be reduced. That means if we are considering an entire beam profile, so in that scenarios, the angle of beam spread in the different area where the intensity we can consider 50% reduction, 20% reduction, or 10% reduction with respect to the central beam axis or a main axis, where the 50% loss will be there, that will be known as a 6 dB down point. If either it will be the 20 dB down point or it will be the at the edge. So according to the point from where you are going to calculate the beam spread, then ultimately the thing is we can using this formula that K into lambda by D, that is equal to D by F. That means the beam spread angle values depends upon here also the diameter of the crystal and the frequency. So the effect of crystal diameter and frequency for the determinations of near field and beam spread, that is vice versa to each other. That means if we are going to increase the crystal diameter, it will increase the near field, but it will decrease the beam spread. So here you can see that the two crystal which is the same diameter but has a different frequency. One is a 5 megahertz and another is a 1 megahertz. 1 megahertz frequency probe has a lower near field values, but its beam spread is higher compared to the 5 megahertz. So depending upon the crystal diameter and frequency, we are selecting the probe as per the job is concerned. So depending upon the thickness and the job geometry or material grain structure, we are selecting the desired frequency such that the maximum penetration is possible. And along with that, we are selecting the diameter of the crystal. Say, for example, if we are considering the normal or tear probe, the normal or tear probe come into the different diameter of crystal like 5 mm square, 10 mm square, 25 mm square. So depending upon the penetration thickness is required and the structures of the material, that is grain structure of material, code is suggested for the selections of the diameter such that near field and beam spread will be under control. In the same way, if we are considering the angle probe, the angle probe can be available in different size, 5 into 8 crystal diameter, or it is will be into the 4 into 5 or 3 into 5. So miniature probe and the standard probe of 8 into 9 we can use for the flat surface and as well as for the lower curvature. So the crystal diameter and frequency is selected in such a way that the near field and beam spread will be under the control. When the sound will be transferred from the material during the transmissions, definitely there will be the loss in energy and as well as the loss in its intensity. The percentage of the loss in their intensity or the energy that will be make the relations of the attenuation law and the formula A equal to A0 into e to the power minus A into Z that we are applying, where uh, A and Z, that is the density of the material, and Z is the acoustical impedance value. A is the thickness and Z is the acoustical impedance value, penetrated thickness or distance in which you are going to calculate the intensity. So A and A0, A0 is the unattenuated amplitude and A is the attenuated amplitude. Different type of material is exhibiting the piezoelectric crystal nature. That means conversion of electrical energy to mechanical energy and mechanical energy to the electrical energy. Both can be done. That means the property is known as piezoelectricity, and that piezoelectric behavior can be exhibited by lithium sulfate, quartz, polarized ceramic, and barium titanate. But individual piezoelectric crystal, we cannot say they are exhibiting all the character. We need a crystal which is a good transmitter of sound, either it's a good receiver of sound, it can operate into low temperature, high temperature, it has a dielectric constant is high, and the thing is it will be not fragile in nature. Mode conversion is not done easily. So in that scenarios, each and every piezoelectric crystal has some advantages and disadvantages. So in that scenario, some alloyed material like that of PZT, lead zirconate titanate is prepared such that all kind of characters, so whatever we have a requirement for the proper sensitivity and resolutions of the probe that has been maintained. There are three type of probe we are using in the industrial application. Straight beam probe. It is the straight beam in the sense it's produce the longitudinal wave in 0 degree, but it's a single crystal probe which is acting as a transmitter and receiver due to the dead zone issues into the lower thickness. Normal probe has been replaced by the TR probe where twin crystal, one as a transmitter and another is a receiver we are using, and a acoustical barrier is there in between these two. In case of lower thickness, less than 20 mm thickness, where near surface resolutions of the near normal probe is very, very less. To compensate that one, we are using the TR probe that is also producing the 0 degree longitudinal wave for the determinations of the defects in your inspection part, which is parallel to the inspection surface like that of laminar type of flow. So in lower thickness, we are using the TR probe, or in case of higher thickness, we are preferring to use the straight beam probe. And third one that is known as the angle beam probe, and this angle beam probe is producing a desired angle of refracted wave into the form of shear wave. In generally, as per the conventional ultrasonic is concerned, we are using 45 degree, 60 degree, and 70 degree angle probe. 45, 60, and 70, it means that the refracted angle is 45 degree in steel, or it can be in aluminum, or it can be in whatever the material it is, and that is written into the probe. Suppose any probe is assigned like that of 45 degree S, that means if we are placing this probe into the steel surface, it will give you 45 degree refracted angle. But the same probe, if it is made for the 45 degree refracted angle into the steel, if we are placing that probe into the aluminium or other material other than steel, definitely refracted angle will be changed. So for the 45 degree of steel, we can calculate what is the incident angle of that piezoelectric crystal, and according to the incident angle and with respect to the velocity of aluminium, we can calculate what will be the reflected angle into the aluminium itself. When we are selecting any probe, the probe has three characters we need to be considered on that. First one is the sensitivity. Sensitivity of an ultrasonic system is the ability to detect the smallest discontinuity. Sensitivity of a probe is measured by the amplitude of its response to the energy reflected from a standard discontinuity. Say we have a 1.5 mm side drill hole in IIW V1 or V2 block, and we are placing a particular type of probe, subprobe A, and we are getting the response from 1.5 mm side drill hole, and we are going to establish the height of that particular reflection to 80%, and for the productions of 80% echo, suppose probe A and its machine is required say 40 dB. Another probe that is required for the productions of 80% amplitude from the same reflector, it may be 25, 26 dB. That means lower dB is required in case of probe B. So then we can say the probe B is much more sensitive compared to the A. Whatever the dB value is less, attenuation loss will be less there, and the chances of the signal to noise ratio will be improved, and defect can be identified in a very high accuracy. So high sensitive system and probe is always preferred. Resolutions means if the two defects are laying into the same location, but the nature of the defect is different. So these two defects, if we need to be resolved properly, that is identified separately, if any system or probe has the ability to identify that one, then we can say it's a good resolution. So when we are selecting any probe or any machine, ultrasonic 2FD, ultrasonic detector, we need to be verified whether the system has the correct amount of resolution is there or not. Each and every probe has a mechanical quality factor which is denoted by Q, and Q is calculated by using the formula F0 by F2 minus F1, where F0 is the central resonant frequency. Whatever the electrical impinge is there into the piezoelectric crystals, the resonant energy. Suppose one probe has a 4 megahertz probe. So in that scenario, the resonant frequency is 4 megahertz, and if the 4 megahertz energy is been liberated, but due to the ringing effect of the piezoelectric crystals, whatever it will be ringing up to certain time period, it will produce the ultrasounds. And if we are considering the 70% with respect to the F0 intensity, that much area, F1 at that minus 70% and uh, uh, another 70% in the rightward direction. So entire frequency for the 70% in extremely left of the beam and 70% in the right of the beam, then this band F2 minus F1, that will be known as the bandwidth, and F0, that is resonant frequency divided by bandwidth, that will give you the mechanical quality factor. So depending upon the mechanical quality factor Q values, the bandwidth is normally determined. Lower Q value has a higher that is known as a broadband probe, and higher Q value, that means it will be known as a narrow band probe. Normally, always we need to be focused our ultrasonic beam in our inspection surface more accurately. And in that purposes, there are two type of focusing is there. One is known as spherical focusing, and second is the cylindrical focusing. So spherically and cylindrically, ground cause are commonly added to the immersion type of probe. That means probe. Okay, so now the ultrasonic equipment, each and every ultrasonic equipment is built up with the these five basic blocks. One is the clock, timer, and synchronizer, transmitter, sender, pulsar, sweep generator, receiver amplifier, and display unit. Entire ultrasonic system is working with the help of these five basic blocks. First one is the clock and timer. It will provide the constant rate of pulses. That means the repetitions of the pulse, electrical pulse to the piezoelectric crystal, that is controlled to the transmitter, and whatever the returned energy is there, that will be into the swift generator. All the electronic functionalities is normally covered by the time base. So the clock timer is making the coordinations of all other blocks with each other. Transmitter with the transmitter high voltage pulses of a short duration to the piezoelectric crystals, and the transducer also provide the reference indication that is known as the initial pulse. And through the receiver and amplifier, The starting of the initial pulse is referred to as a electrical zero, and it is distinguished by the acoustical zero when we'll be lifting the probe from your inspection material. Whatever the echo that will be present into the screen, that will be known as the electrical zero. And when we are putting the probe into an inspection part, the initial echo will be there. So in between the time lag of electrical zero to the mechanical zero or the initial echoes, that will be adjustable by using the zero control in your equipment. All the ultrasonic equipment has a shift generator, and this makes the electronics of the ultrasonic machines for the movement to the left to right in a specific speed, forming a sweep line. Receiver unit is normally receiving the returned energy of ultrasound and transformed this returned energy into the from the radio frequency to the video envelope by filtration and amplification. The display unit, that is known as the CRT, it's nothing, it's a picture tube like that in television, and it's a horizontal and vertical deflection plates. And the CRT is a fluorescent screen where electron is generally bombarded and the brighter image is there into the scene. Each and every ultrasonic equipment has a PPR, pulse repetition frequency, depending upon the material thickness, structures, and whatever the crystal size and frequency is there. It is determined by the equipment by default that what will be the repetition frequency of the electrical energy, electrical pulses, such that near field resolutions and distinguishes of the initial pulse and backwall and defect echo can be done correctly. Pulse energy, it is from the 200 volt to up to maximum 1200 volt is supplied to the piezoelectric crystals for the vibration to its resonance frequency. When we are connecting a probe to the piezoelectric crystal, by default, it is calculated by the machines, and that much amount of voltage of pulses is supplied. Each and every ultrasonic equipment has a damping control to control the electrical noise or excessive vibratory noise. That's one. So any kind of electrical interference or electrical noise is internally damped by the machine hardware and software itself. Each and every ultrasonic equipment has a gain control unit. Gain control, it also indicate as a dB control. That means when the reflected energy is returned back to the ultrasonic machines and it is not in a exact intensity to be displayed into the CRT screen. To increase the amplitudes, there are some gain and dB control unit is there. If we are going to increase the dB of the ultrasonic machine, height of the echo will be increases. And if we are going to decrease all the echoes that will be presentable forms that which are into the presentable form, that will be increased or decreased accordingly. Each and every ultrasonic machines has a reject control unit such that we can able to reject a specific percentage of height of the reflected echo. In some scenarios where surface roughness is very high, internal grain structure is coarse in nature, internal scattering is maximum, and thirdly, if there is a possibility of electrical noise, so in that scenario, if it is very difficult to interpret the data with respect to the operator or the inspection authority, then there is a understanding between these two, and we can take a specific percentage of height, 2%, 3% as a reject control. But in generally, it is not recommended to use the reject control during your inspection. When we are connecting a probe with your ultrasonic equipment, whatever the bandwidth of the probe is there for the receiving and transmissions of the signal from that particular probe, your ultrasonic machine will by default, it will adjust its bandwidth for that particular transmission and receiving capabilities. And distance amplitude curve or DAC, that is the general functionalities given into the all digital ultrasonic machine. DAC stand for distance amplitude correction. Suppose one reflector, if it is striking by the ultrasonic beam in different sound path or different beam path, definitely there will be the changes in their amplitude. And these changes is occurred due to the sound traveling path, and with respect to the sound traveling path and the attenuations of the material, it can be varied. So the DSC or distance amplitude curve is we are taking as a reference for the decision of acceptance or rejections of any kind of reflection getting from your inspection part. Each and every ultrasonic equipment is containing some delay control unit and range control unit. Delay control means if there is a delay in between the transmission time lag in between the electrical energy and mechanical transmission, that can be adjusted by the machine's delay also. Range means if we are going to adjust the sound traveling path according to the horizontal scale, we can make the proper range. And ultrasonic equipment has a gating control unit. Gating is a particular area of your CRT which need to be much more attention we are giving. There are two gating system into the ultrasonic machines. Gate is the electronic cursor. We are placing it into a particular sound path and particular percentage of height of the returned amplitude. When any kind of echo which is crossed the gating or touch the gate, all the numerical calculated values, that is surface distance, depth, and beam path, will be calculated itself by the machine, and it will be displayed into the machine screen. For the calculations of the gain or dB, normally we are using the formula 20 log of H2 by H1, where H2 by H1 is the ratio of the echo heights. 2 is to 1 incremental or decremental step of the echo height, that is equivalent to the 6 dB. 4 is to 1 ratio of changes into the intensity, that will be the 12 dB. 5 is to 1 equivalent to 14 dB, and 10 is to 1, that is the 20 dB, and 100 is to 1, that is equivalent to 40 dB. Each and every ultrasonic machine has a dB control unit in two incremental and decremental state. It's a fine gain control and coarse gain control. Ultrasonic equipment data display is normally occurred into the three type presentation: A, B, and C scan. A scan is the general presentations of your data with respect to sound traveling path into the x-axis and in and amplitude of returned energy in the form of echo into the y-axis. B scan is a scan presentations or the display of a profile view, that is cross-sectional view of your test specimens. Only the reflected depth in the cross-section of the linear dimension can be determined. The limitations of the B-scan display technique is that the reflector may be masked by the higher reflector near the surface. C-scan presentation basically using in the advanced ultrasonic machines where planar view of your test specimens can be done. C-scan representations are produced with the automated data acquisition systems such as in immersive scanning or in phase array system. Use of A-scan is a conjunction with the C-scan is necessary when depth determination is desired. When we are about using the normal or tear probe, the sound is transmitted in the 0 degree, and the sound traveling path will be multiplications of the thickness of your inspection part. But in case of angle beam probe, it will maintaining a angular distance. The first striking of the refracted beam of the sound beam of the CR wave when the sound path, that will be known as the half beam path, and that half beam path we can be calculated by using the formula T into sec theta. And in that respect, the distance from the perpendicular line of the reflection to the center of the probe, that is known as the surface distance, and the front face of the probe to the central perpendicular line of the reflector, that is the skip distance, and the distance between the probe center, a probe index, to the entrance or the end of the probe, that is the XO value. So surface distance is the summations of skip distance and XO value. Skip distance we can calculate by using the formula T tan theta. If any reflector is there with indicating the beam path as a BP, so in that scenario we can calculate the surface distance equal BP into sine theta, and the depth that will from the top of the inspection surface it will be calculated by BP cos theta. For the determinations of the defect and interpretations of the defect, and how to identify the exactly from where the reflector is coming, beam path, depth and surface distance value is very important. So when we are using the angle beam scanning for the weld inspection, all the desired distance need to be much more accurate. So that's why during the interpretations of the ultrasonic scanning of the weld inspection by the angle beam probe, surface distance, beam path, and depth, these three value plays a very important role. And when any echo or any kind of reflector will be under the gate, all the calculated values of SD, surface distance, depth, and beam path will be calculated by the machine itself. And ultimately, according to that data, we can easily analyze from where the reflector is there. So 50% interpretations were carried out for the identifications of the defect from these three numerical values. Thank you for the uh, listening of this part B. In the continuations of ultrasonic testing in part C, we will discuss the first initial calibration process and how we will be standardize the equipment and the probe with respect to the code requirement of ASME section 5 article 4, and then how the reference block is prepared, what are the type of reflector we are using, and from that particular block how you will be draw the reference line or DSC or DGS, and according to that we will be inspecting our part and take the decision regarding the sizing and identifications of the defect. Thank you for the participation. Thank you.